everyone. Welcome back to Computational Nanophotonics videos. I'm Josh, and today I want to talk to you about running simulations of periodic structures using Lumerical's FDTD simulation software. So what do I mean by periodic structures? Well, the simplest example, in my opinion, of a periodic structure is just Fresnel reflection and refraction. So we have light traveling from material 1 into material 2, and some of the light will get transmitted, some of the light will get reflected, and we don't actually need FDTD to do this sort of calculation because we have the Fresnel equations. But this is an example of a periodic structure because on this side and on this side, we assume that there's infinite periodicity. So we assume that material 2 goes off forever in this direction and in this direction, and the same with material 1. It goes off forever in this direction and in this direction. So if we wanted to simulate this sort of structure using FDTD, all we have to do is actually just kind of set it up like this and then apply periodic boundary conditions on either side of our domain. All right, the next most simple object that's periodic is a thin film, some sort of thin film experiment. So we have light coming in from material 1, and then there's a thin film, material 2, and it gets transmitted into material 3. Again, we don't need to use FDTD to do this sort of calculation to know how much light gets transmitted and how much light gets reflected, because there are analytical solutions for this. Namely, the transfer matrix method can be used to do this sort of calculation. Or again, with Lumerical, we could just, or with FDTD, we can just set up our FDTD simulation domain like this and apply periodic boundaries on either side. And again, we can do any number of calculations using this. And finally, and probably the reason why you're here, is we also have Metasurfaces and metalenses. So these are typically periodic structures that consist of two or more layers of material and then some sort of nanoparticle structure on top. And typically the nanoparticles are periodically placed. All right, so here's kind of a paper that I just found. I just Googled periodic metasurface, and here's a diagram from this paper here. I haven't actually read this paper. So typical student citing a paper without reading it. But yeah, so if we zoom in here at their diagram, though, what do we have here? Well, we have some sort of, I'm assuming some sort of dielectric block of material. And on top of that dielectric block of material, we have these metallic patches. So these are probably silver and gold nano patches. But the point that you need to realize here is that if we kind of zoomed in on one of these patches, we can see that it's, well, first of all, it's periodic. So there's a unit cell that you can just draw a square around one of these patches, and that's your unit cell. And that unit cell is much smaller than the spot size of your laser. So instead of running a full simulation of this entire metasurface and sending in some sort of Gaussian beam, we could actually simplify simulating this sort of structure by just looking at one unit cell and then applying periodic boundaries. So this is pretty much what I showed here, just kind of more of a 2D version of that here, where this is actually, so if these boundaries are periodic, then what I'm actually simulating is an infinite array of this gold nanostructure on these two materials. And so today, in this tutorial, I'm going to kind of walk you through setting up a metasurface simulation using Lumerical. And I'm going to start with just basic Fresnel reflection and refraction. So I'm going to actually put in a silver surface down here, a silver material down here, so we can see what the reflection spectrum of silver looks like. Again, you could do this using Fresnel reflection and refraction, but I'm going to do this using Lumerical just to kind of show you. I'm going to show you how to do some sort of thin film calculation like this using two dielectrics. So I'm going to remove the silver, and I'm probably going to make this silicon and this silicon dioxide or something, because that's going to be more interesting to look at when it comes to thin films. And finally, I'm going to show you how to do a full-out metasurface like this. All right, so let's get started. So let's first open up our Lumerical FDTD software. All right, so for now, I'm assuming that you guys know why you want to do some sort of periodic simulation. All right, You're probably here because you want to know how to simulate metasurfaces, and I'm not going to teach you metasurface theory or anything like that. I just want to show you how to set up the simulation and how to get the job done. So the first thing I'm going to do, like I did in my previous lecture, or my previous tutorial, sorry, is I'm going to set the length units to be nanometers. So settings, length units, click on nanometers. That's just my personal preference. You then click on the simulation box and you'll get this big orange box. We right click on that, we edit object. As before, we don't really change anything here. You could set the background material to be any material that you want. I'm just going to let it be vacuum, so with the dielectric with a refractive index of 1. The geometry, okay, good. It's centered at 0, 0, and 0, so that's great. So I want, all right, so I'm gonna kind of define some terms here. So I want the light to propagate in the x direction. So I'm going to call this kind of the x direction the long axis. So this is the x direction is the up and down direction, and the y and z directions are going to be periodic. So here in this picture, for example, the x direction is this black arrow, and the y and z direction are up and down here. So those are the periodic directions. So because x is the propagation direction, I want it to be longer than the other two, so it's going to be 1000 nanometers. And I'm going to set the periodicity to be 200 nanometers in the y direction and 200 nanometers in the z direction. They don't have to be the same, but I'm setting it to be the same. I'm going to choose a uniform mesh, and I'm going to pick the mesh size to be 5 nanometers. So that's the step size. So the simulation domain is going to be 200 cells in the x direction, so that's just 1000 divided by 5, and 40 in the y and z direction, so that's just 200 divided by 5. In reality, a 5 nanometer step size for some sort of nanoscale simulation is pretty big, so you may want to do some sort of convergence testing, but the reason I'm setting it to be 5 is just so the simulations run in this video, because sometimes the simulations can take a long time. All right, finally, and arguably the most important part, is setting the boundary conditions. So in my previous videos, I was doing scattering problems, so I wanted the light to go off to infinity in all directions. Well, for a periodic structure, that's not quite what we want. So let's see, let's kind of look at this simple case here, right? So we have light comes down in the x direction, it hits this material, and it's gonna, let's say, some of it will be reflected and it'll go off here. So up in this direction, in the x direction, we want the light to travel to infinity, all right? We don't want the light bouncing back into the simulation. We want the light to go off forever. So in the x direction, we want there to be a PML, a perfectly matched layer, which basically will just absorb the light going out so it won't come back in. So in both of the x directions, up here and down here, we want PMLs. Because our structure is periodic though, on this edge and on this edge, we want it to be periodic boundary conditions. So in the x boundary conditions, we just want these to be PMLs, so that's the default. In the y direction, we want it to be periodic. So if you put one of them to be periodic, the other y will be periodic by default. And similarly with z, we want it to be periodic. And we don't need to change any of the advanced options, so we just click apply and OK. All right, so here's our simulation domain. Click on the magnifying glass over here, which will recenter everything. And what Lumerical does is they take your periodic boundaries and they make them blue. So that means that there's a periodic boundary condition here. And this big orange blob is your PML. All right, so again, we want the light to be traveling in this direction, and we want it to be periodic in this direction. And of course, so this is the y direction, up and down. And of course, in this viewing window, we have the XZ view, so this is the Z going up and down here. So it's periodic in Y, and it's periodic in Z. Hopefully I've hammered that in enough. All right, so next we want to put in a source. So in my previous videos, I was doing scattering problems, so there are PMLs in all directions. So I used total field scatter field source. So now I'm going to use a less general version of that, and it's just going to be the plane wave source. So this is what you want to use when you have a periodic structure. All right, and right now, so I just click on the plane wave source, and by default, it puts in a plane wave source that points in the Z direction. Again, we want ours to be traveling in the X direction, so we need to change some things here. So we're going to edit the object, And the injection axis, we want it to be X. And we want it to travel in the forward direction. All right? We go to geometry. All right, so now is where we set everything. So we make sure that it's all centered at 0. So Y centered at 0, Z centered at 0. Because our Y direction, because our simulation dimension, our simulation size, sorry, in the Y direction is 200 nanometers. I'm just going to set the source to be that large. Same with the Z, 200 nanometers. And in the X, I just need to set the position. So I want it to be over here. I want the source to be down here. So that's going to be, let's say, minus 400 nanometers. Click apply, and here we go. We now have our source. It's pointing in the X direction. It's polarized in the Y direction. That's what the blue arrows show. And it starts over here. Okay, next up, we want to, so my first simulation is just going to be basic Fresnel reflection and refraction. So I now need to put in a material down here. And as I mentioned, I'm going to make that silver because silver has an interesting reflection spectrum. So I'm going to put in a rectangle. And here he just shoves in a block into our simulation. So we need to do some editing here. So the geometry, make sure it's all centered at 0. That's good. We want it to fill up the periodic direction. So we need to be 200 nanometers by 200 nanometers. Actually, you can make this larger. So I can say, let's say 240 nanometers and 240 nanometers, let's say. And so what's going to happen, so let's just apply that. You can see that it actually sticks out of the simulation domain a bit here. And that's okay. The simulation software is smart enough that it'll cut off these edges that hang out. So don't worry about that. All right, as for the X direction, we want it to go off to infinity in this direction. So I'm going to set, well, actually, I'm going to set the X geometry using the X min and X max. So I'm going to set the X min to be 0. So that means that the top end here will be halfway through the simulation. And I'm going to set X max to be 600 nanometers. So apply that. So here we go. So it starts off halfway through our simulation domain and it sticks out again, which again, not a problem. The simulation will cut that off for us. All right, as for the material, I promised silver, so let's do that. So you could set a dielectric constant or you can set a material model. So I'm going to set silver Johnson and Christie material model. All right, so we click apply that and it actually changes the color for us to a grayish color. So that represents your silver. What else do we need? Well, I promised you the reflection spectrum of silver, so let's put in a power monitor up here. So what the simulation is going to do, it's going to send in a plane wave, it's going to hit the silver, and the silver is going to reflect the light back, and we want to know how much light gets reflected. So we're going to put a monitor back here to kind of calculate the power that goes backwards. So that'll tell us how much light is reflected, and therefore give us the reflection spectrum. Okay, so here is our power monitor, and it's completely wrong. It's not what we want at all. So we go into Edit Object, go to Geometry, and we want it to be a 2D X normal. Okay, we want it to be behind the source. So the source is at minus 400 nanometers, so let's put this at minus 450 nanometers. And because our simulation domain is 200 by 200 nanometers, I'm just going to set these to be 200 and 200 nanometers. Data to record, this is all fine, this is all fine. No need to change any of that. Go into set global monitor settings. So right now it's set up so that this power monitor will calculate wavelengths from 400 nanometers to 700 nanometers with 5 wavelength points. That's not a whole lot. If we want a spectrum, we want at least 20. So I'm actually going to say let's go with 40 frequency points. So apply this, okay. So let's go back. Also, it's only going from 400 nanometers to 700 nanometers. So that's the visible range. But silver, a lot of its interesting behavior happens in the ultraviolet. So what I want to do is I'm going to actually set this wavelength to be lower. So I can't do it here. So what I have to do is I have to go into the source, Edit Object, go into frequency/wavelength, and I have to set it here. So I'm going to set the source. I want the wavelength start to be 200 nanometers. So I want to go into the ultraviolet. So I can get that kind of that neat behavior, catch that neat behavior as silver. So if I click apply, go here, go back to the monitor, go back into the global monitor settings, you can see now that it's measuring wavelengths from 200 nanometers to 700 nanometers. Perfect. Apply, okay. And the last thing I'm going to do, as I always do, is I'm going to put in a movie monitor. It's a lot bigger than the simulation domain, but that's okay. It'll truncate all the rest of this stuff out. So now our simulation is ready to run. Oh, actually, no, it's not. Sorry, 1 second. I know this from experience. Data record X normal, 2D X normal. Okay. Yeah, okay. So what's actually going to happen here? All right. I'm going to explain something before I run the simulation, just so it's not confusing when we look at the results. So again, what are we expecting to see? We expect the light to come down. It's going to hit the silver, and we expect the silver is going to reflect a lot of the light because silver is highly reflective. And so we expect the light reflected to have a pointing vector in the negative x direction. All right, so the pointing vector is going to be in the opposite direction of this pink arrow for the reflected light. However, what this monitor is going to do is it's going to calculate the pointing vector in the positive x direction. Just by default, that's how the power monitors work in Lumerical. So if you put a x normal monitor, it's going to calculate the pointing vector in the x direction. So when I run the simulation, when I look at the results later on, what I'm going to see is I'm going to see that the spectrum is going to be upside down. It's going to be negative of what we want it to be. So I'm telling you that now just as a warning, because I don't want you guys to be confused. If you put the power monitor here and you want to know what the pointing vector is in the negative x direction, you're going to get that negative result. So I'm going to show you how you can flip that in post-processing. But now we're just going to run the simulation. Okay, so we need to save it. So I'm going to call this Fresnel. Save. All right, and now it's going to run. So as usual, it's overestimating the amount of time it's going to take. So it says it's going to take 13 minutes. Because it's a small simulation, so as I pointed out earlier, it's 200 by 40 by 40. It's going to take a few seconds, actually, so it's not that big. But what we expect to see, so what we want to see is the reflection spectrum of silver. So here's a picture of the reflection spectrum of silver. It's just this gray line. So we expect there to be a dip in the reflection spectrum at around 300 nanometers. And then past that, up into the visible and into the infrared, we expect that the reflectivity will go up to around 90 and all the way up to around 100 nanometers up into the infrared. All right, and this is not surprising. Silver is highly reflective in the visible. That's why if you have some sort of pure silver sample and you look at it, you'll see yourself being reflected back at you because it's highly reflective in the visible. All right, so the simulation finished running. And now we can, first let's watch the video because that's what makes FDTD exciting. So this is stored in, so you got to go to the folder where you saved your, your Lumerical file. So I saved it in Python scripts for some reason. And so here's the movie monitor. I'm going to open it with Windows Media Player because the Films and TV app doesn't play this type of video file for some reason, but Windows Media Player does. All right, so what are we looking at here? So here we have air on this side, and we have the silver on this side of the white line. And you can already sort of see it starting here, but what's going to happen is we're going to have a plane wave coming in, it's going to hit the silver, and it's going to reflect. So here's our plane wave coming in. It hits the silver, and we see some interference happening, and then it's reflected backwards, and it goes off to infinity. And as we expected here, because silver has such a small skin depth, it's reflecting most of the light. So not a lot of light gets into the silver. In fact, if we were to measure the transmission down here, it should be 0 or at least close to 0, because any light that does get transmitted is inevitably absorbed. Okay, so now let's look at the reflection spectrum. So to do that, we go to our power monitor, we right click, we click on visualize, and we click on T. So T is going to give you the spectrum, the transmission or the reflection spectrum. All right. And as I told you, it actually plots it upside down. It plots it negative because, again, it's calculating the pointing vector in the wrong direction. But all we need to do to fix that is we just click on scalar operation, and you click on negative real. And there we go, it flips it for us. So this is what we see. We see that we get our dip at around 300, maybe 280 nanometers here. You should be around 300 nanometers, but that all depends on the material model you're using. And of course, for the visible, the reflection goes up into around the 90% range because it's highly reflective for the rest of the visible. The reason why there's a dip here, if you're interested, is because of interband transitions. So it's around here where some of the valence band electrons get promoted to the conduction band. So there's some absorption that happens in this region here. So if there's light being absorbed, then there will be a dip in your reflection spectrum. Awesome. So there we go. I just showed you now how to calculate the reflection spectrum of a periodic structure. Of course, the periodic structure is quite simple. It's just a silver bulk half plane. So let's make things more interesting now. So now we're going to do the thin film. So I'm going to keep this rectangular prism, but I'm going to change it to a dielectric material. So object define dielectric, and let's make it 1.5. So it's going to be something like glass. All right, so we click apply, and now we have a dielectric material, a dielectric index 1.5, and I'm going to add in another rectangular prism. All right, we're going to edit this object, and we're going to center it at 0 here and at 0 for Z, and I'm going to make it 240 by 240 nanometers like I did with the other rectangular prism. Again, it doesn't have to be bigger than the simulation domain, but as long as it's 200 nanometers or larger, it's fine. And I'm going to center it in X at 0, and I'm going to make it, let's make it 200 nanometers wide. No, let's make it 100 nanometers thick. All right, and then for the material, we want it to be, I'm going to make this a high index dielectric. So we're going to go 3.9 refractive index. So this is more like silicon. Okay, so we press OK. All right, didn't really change the color that much, eh? All right, so instead of that, then what I'm going to do, so I'm actually just going to pick silicon out of here. All right, so silicon, so let's just, here, silicon. So apply, there we go. All right, so now we can actually see the thin film. All right, so we have a dielectric layer here of some sort of dielectric index of 1.5 down here. We then have a silicon layer up here, and you can see there's a bit of an overlap. So I'm going to fix that by just dragging. You know what? To fix the overlap, I'm just going to pull this one here up a bit. So let's set the X minimum to be. Actually, set the X max to be. Okay. X minimum to be minus 100. And set the X max to be 0. Apply that. There we go. So now there's no longer any overlap between the two. All right, but this here is just our thin film experiment here. So our material 1 is air, material 2 is silicon, and material 3 is our dielectric of 1.5. All right, and this time I want to calculate the reflection spectrum, but I also want to know the transmission. So I'm going to get another power monitor here, and we're going to do what we did before. So it's going to be 2D X normal, and I want to push this all the way down here, so I'm going to put it at 450 nanometers. And we're going to set this to be 200, and I believe everything else, 40, perfect. All right, awesome. Geometry, apply. Okay, there we go. So we now have a power monitor down here that'll tell us what the transmission spectrum is. All right, so now let's run this simulation. Okay, so this one might take a bit longer just because of the silicon layer here. We expect that there's going to be some Fabry-Perot resonances happening in the silicon because it's such a high index dielectric. So light's going to be bouncing back and forth between the air silicon interface and the dielectric silicon interface. But we will see how long it actually takes. Oh, it actually didn't take that long. That's quite nice. All right, so let's now watch the movie again. So we go into our folder where we save the file, and we're going to open this again with Windows Media Player. All right, so first of all, we have here's our silicon layer highlighted in white. We have air on this side. We have dielectric material on that side. So let's see what we get. So we have our pulse comes in here. Okay, so actually most of it's still reflected, but we do get something, some gets transmitted through here, and you can actually see there's some resonating happening here. There's still some light coming in and out, So that's neat. But it's not as exciting as I thought it would be to look at. Oh well. Let's now take a look at the spectra. So we're going to go into our reflection monitor, and we're going to visualize T again. We actually have to flip it one more time. So this is the reflection spectrum of this thin film setup. So you can almost see that there's all these dips, right? So these are kind of your Fabry-Perot resonances here. And if we look into the transmission spectrum, this one we don't have to flip because it is pointing in the right direction. We can see that, whoa, we can see here that it's almost zero transmission down here for these lower wavelengths. As you go up here, the transmission increases. So there you go. There's your transmission spectrum of this thin film setup. And finally, I promised you a metasurface, so I'm going to give you a metasurface. So all I'm going to do, I'm going to keep this setup here, but I'm just going to add a gold nanoparticle on top here. All right, so we're going to go back into layout mode. We're going to get our structure. So this is a block of material again. I'm going to edit this object. Again, center everything at 0 to start with. 0, 0. So this time for the Y direction, let's make it a square nanoparticle of 100 nanometers by 100 nanometers. And as for the thickness, okay, so I just need to think about the geometry for a second. All right, so we have our silicon layer, which is 100 nanometers thick, so it goes from 0 to negative 100. So we need our X maximum here to be negative 100, and our X minimum. So let's make this a thickness of 50 nanometers. All right, so we want this to be a 50 nanometer thick gold particle. So we now go into material, and we're going to click on golds, and I'm going to say gold CRC. Actually, no, gold Judson and Christie. That's a good model. Click apply, and okay. Now where did the particle go? I see. I didn't put it. All right, how thick did I make this layer? So what's the geometry here? It goes from 0 to negative 100. Okay. This one here, geometry goes from negative. Oops. Okay. Okay. I want this to be from negative 100 to minus 150. Ah, there we go. Sorry about that, guys. All right, so now we have our gold nanoparticle on top of silicon, on top of some sort of dielectric material. Instead of calling this some sort of dielectric material, let's actually make it a material. So I'm going to make this silicon dioxide, which has a similar refractive index to 1.5. I believe it's more closer to 1.45. Where is it? Silicon dioxide, also known as glass. Okay, so there we go. This is a metasurface. And if we kind of look, now the 3D render is not that nice because you can barely see the gold particle. But yeah, you have glass, you have a silicon layer, and you have a gold particle. And let's just add the mesh on top. So yeah, the particle's big enough that it takes a few mesh points. So that's quite nice. All right, let's run the simulation. So run. And again, all we're actually simulating here is just a periodic array of gold nanoparticles on top of a silicon thin film and a silicon dioxide substrate. And this here is actually, like, this setup here is what I use for a lot of metasurface simulations that I do for real research. So this is actually a useful setup to remember. All right, silicon thin film, silicon dioxide substrate with gold particle on top. Of course, I don't usually do a gold rectangular prism. A lot of my stuff I use like gold triangles and stuff. But anyway, this is the basic metasurface simulation setup. All right, and it runs pretty quickly. It should be finishing now any second. Come on, you can do this. But again, when you're doing any sort of plasmonic material like gold, the step size of 5 nanometers is way too big. All right, you want to be like 2 nanometers or less. All right, but again, I just wanted the simulation to run in a decent amount of time. Okay, so let's watch the movie. So we're going to play this using Windows Media Player. All right, so here's our gold particle. So look at that. That's neat. So you can see that the gold here resonates here. There's some resonance happening at the gold. Let's watch it one more time here. Oh, okay. Sorry, I need to rewind it. So again, we have a pulse light coming in here. It hits our gold. Some of it gets transmitted through the silicon. But yeah. All right, so let's go back to our Lumerical. And let's look at the reflection and transmission spectra. So here, this is the reflection, visualize T, and again, negative. There we go. And there's your transmission spectrum of this metasurface. Similarly, you can look at the transmission, which almost looks the same as without the gold particle. Oops. Redraw. There we go. Okay, so there you go. This is the basics of how to do metasurface calculations using Lumerical. I have time, so why not just kind of go into some more basic stuff here. So let's say you want to do some post-processing on this data. Maybe you want to save this data to a text file. Yeah, you want to save this data to a text file and maybe plot it in MATLAB or using Python. You can just click this button up here, export to text file. So I'm going to just call this Spectrum, and it saves it as a text file. Awesome. All right, so let's go into MATLAB here. Let's go into Documents, to the same folder where I saved it, which was in, ironically, Python scripts. And s equals import data spectrum.txt. Okay, let's see what this is. Okay, so s is equal to s.data, and we're gonna just plot s. So I believe the first row is probably going to be the wavelength. The second row is actually going to be the spectrum. Yeah, so over here. There's the spectrum. So you can now open it up in MATLAB and play around with this however you want. Make the plot as beautiful as you need to be, or whatever. So that's something useful. What else could I show? Okay, let's do angled incidence waves. How about that? So we want a wave coming in at an angle. So the way we're going to do that is we're going to go into geometry. So if you want angled incident waves, if you want to put in waves at an angle using FDTD with periodic boundary conditions, it's actually not as easy as you would think it would be. So switch over to layout mode. Instead of periodic boundary conditions, you want to use a block boundary condition. All right, block boundary condition and a block boundary condition. Apply that. Okay. And now with your source, you go and edit object. And now you can probably set your angle here. So let's say 30-degree angle, apply that. Okay. Yeah, so now it's going to put in light at an angle going this way. And what block boundary conditions does is it makes all of your fields complex. Because, again, inputting light at an angle using real value fields with periodic boundary conditions, it gives you causality problems. So on one boundary, you need to know what's happening at the other boundary at a previous time step. But on this boundary, I need to know what's happening at this boundary at a future time step. All right, we don't know the future. So that's what causes the problem. And the solution is using complex numbered fields. The method, actually, maybe just Google block boundary conditions Lumerical. There we go. So yeah, just go to their webpage and they explain to you the basic theory of all of that there. But it's a bit tricky, so maybe I won't get into this today because there's a bit of explaining that needs to be done, a bit of theory that needs to be covered. Yeah, sadly, it's not as easy as just inputting waves at an angle. But yeah, that's something you need to. If you want to do periodic boundaries with angled incident waves, just Google block boundary conditions and follow the directions set forth by Lumerical. Because it's not all that easy. Anyway, so this is probably where I'm going to end the video. I'm sorry that this was a bit more, that this was kind of rushed, wasn't very planned out, but hopefully you guys find it useful, and let me know if you have any questions in the comments. Thank you so much.